welcome back to AP Stats Notes Online. I'm going to move into Chapter 10, which is where we start looking at two groups, proportions or means of two groups. And very often that's exactly what we want to take a look at. If we want to compare the effectiveness of two different treatments in an experiment, right? We might apply those two treatments and look for the difference in their effectiveness. If we want to know if there's a difference in the proportion of men versus the proportion of women that are going to vote for a political candidate, we would take a look at sampling from two different populations and comparing them. And very often the most logical and the most common way to compare those is to subtract them. And so we're going to constantly talk about the difference between either the population mean or population proportion for two different groups. The good news is, as I mentioned in class, is that a lot of what we're going to do with two groups looks a whole lot like what we do with just one group or one proportion or one mean. So not too much of a stretch here, but we'll talk about those differences. And so, first question, what is meant by the sampling distribution of the difference between two proportions, right? And your book does a very good job of providing three fathom dot plots, which are simulations. And the first two are proportions from individual populations, the sampling distribution of a particular p-hat for two different groups. And then the third one shows you what happens when you combine those two sampling distributions. And we touched on this a bit in class, but what we mean by that is what we've been doing prior to this is looking at one group, one population, sampling that population, and taking a look at the proportion of whatever, right? And then we create a sampling distribution of a bunch of p-hats. And we talked about this. Sampling distributions are nothing more than how often your sample proportions would take a certain value, and what those values actually are. And so you'd have a sampling distribution for a single population, and I'll sketch a normal curve that by no means need to be normal. The sampling distributions is not. So this might be from group 1 or population 1. And then we'll do it for a second group, and very often we'll do males and females. We'll create two groups that would have a systematic difference for whatever reason, whether it be that males are logical and females are illogical, or that males are rational and females are irrational. But anyway, we'll do this. We'll separate the population, or we'll create or look at two different groups because they're systematically different in some way. So this might be your group 2. It would be the proportion of whatever, it'd be the same measurement, right? And the question becomes, what if I want to compare these two? What would the sampling distribution look like if I were to compare these two? And again, the most logical way to do that is to look at their difference. Is there a difference? What's the difference in these two groups and the proportions of these two groups? Okay? And so that's what we're talking about with this idea of the sampling distribution of the difference between two proportions. Okay? And so what is meant by that? What it does is it describes the possible values of taking those sample proportions and subtracting them. So it gives us the possible values of P1 hat minus P2 hat and how often those values will occur. If we get a difference of 10%, how often would we get a difference of 10% if we continue to sample, right? And so that's what we're talking about, is the possible values of the difference and how often they're likely to occur. So what about the shape, center, and spread? Very often in our inference procedures to this point, we want to know what the shape, the center, and the spread of that sampling distribution, of those sampling distributions, is going to be. And if we consider the fact that we would basically create a sampling distribution for the individual groups first, then we can apply some of the rules that we've used in the past to talk about if we were to combine those by subtraction. Okay? Because, again, p-hats are nothing more than random variables. Every time I take a sample, I could very well get a different numerical value, and that's pretty much the definition of a random variable. So what is the shape, center, and spread of the sampling distribution of p1 hat minus p2 hat, and what are the conditions that need to be met? Okay? And so shape. First of all, shape. If the sampling distribution of the first group is approximately normal and the sampling distribution of the second group is approximately normal, then we know that when we combine two random variables, the shapes of their distributions do not change. And so as long as those two individual distributions are approximately normal, the combination, the distribution that shows their combination, is going to be approximately normal as well. And so, and the way we do that with proportions is to make sure that the successes and failures, remember these are your successes, and these are your failures, but that for both groups, these are both bigger than 10, right? It's what we've been doing before, but now we've got to make sure that that's true for both groups, okay? The center, as we mentioned in class, the center, when we combine two distributions by subtraction for random variables, we simply subtract the centers. And so, again, using the idea that p hat is supposed to be an unbiased estimator, and therefore the center of your sampling distribution, then it would make sense to find the center of the difference distribution to just subtract those two, p1 hat minus p2 hat. The spread. What we're talking about with spread is the standard deviation of the sampling distribution. And we can calculate that with a lot of confidence as long as the population is bigger than 10 times the sample size. And it's important to note this has to be true for both groups, for both samples. Okay? So we're going to have to make mention to that. We're going to have to assume that there's so many males in this group, and we're going to have to assume that there's so many females in this group if we're talking about the difference between males and females. Okay? And so, and what you'll see here in a minute is that a lot of these conditions come from, are going to look like what they did for the single group, single proportion inference procedures, only we've got to make sure we're talking about both groups. Okay? So, we get to our first inference procedure, and that's confidence intervals. What if I wanted to estimate the difference in the proportions of two groups, proportions of whatever, right? President Obama probably would like to know what the approval rating difference between men and women might be, or Republicans and Democrats might be, or Democrats and independents might be, right? And so it would be helpful to have some sort of estimate as to what the difference in those approval ratings might be, and he can sort of tailor his message to try to convince and sway the group that may not approve as much, right? I don't know. There are a lot of different situations where you'd want to do this. We'd want to estimate the proportion difference in two groups. Okay? And so to do that, we're going to create a confidence interval. And we know what confidence intervals look like. Okay? The formula for a two-sample z-interval, and that's what we're talking about now, called a two-sample z-interval because we're looking at two different samples. We're looking at two different groups. Called a one-sample z-interval before because we were only looking at one group and trying to estimate the proportion for one group. Okay? Well, the formula is still the same. We're going to take our statistic, and then we're going to add and subtract the margin of error. Now, where those come from is going to look a little bit different. Okay? And we can even project this back to our one sample stuff. So more specifically, our margin of error comes from taking some critical value times the standard error. Now, our statistic is also our point estimate, right? And so we'll talk about this a little bit more in a second, but obviously our point estimate needs to be that single value that we would believe to make the most sense to be the true difference. And so that's going to have to be subtracting our 2 p-hats, and we'll look at that more in a second. The standard error, where is that going to come from? Right? Well, it's simply the standard deviation of our sampling distribution just like it was before. Okay? Only we're going to use p-hat in place of p. Now, what does that mean? Well, let's go back up and talk about the standard deviation of our sampling distribution. Okay? What would that look like? Well, I'll create a new page here, and if you want to try to find a margin to draw this in, it might be helpful. But like I said before, we're going to take a look at 2 distributions, and we're going to combine them into one big difference distribution. And we've already talked about it. This is normal. This is normal. Then doing P1 minus P2, P1 hat minus P2 hat is going to be normal. If the center here is P1 hat and the center here is P2 hat, then the center here is going to be, I've already put it in here, just their difference. Again, when you combine 2 random variables, shape going in is the same, shape coming out is the same as shape going in. To find the new center, we simply subtract the centers of the 2 individual distributions. And then our standard deviation, right? There's going to be some standard deviation, and I ought to change this into the right notation. Since these are sampling distributions, I could get myself in trouble with notation here, right? But we kind of get the point. Okay? Now, this sampling distribution is going to have its own standard deviation. This sampling distribution is going to have its own standard deviation. And when we come up with the standard deviation of the difference, we have to apply the rules of combining 2 random variables. And what this comes from is the fact that variances add. Remember, when we combine 2 random variables, the variances add. The standard deviations are more of that Pythagorean theorem looking thing. In other words, if I want to find this standard deviation, I've got to take the individual variances, right, which is squaring the standard deviations. Okay? And then to go from variance to standard deviation, we have to square root. So we have to add a square root here. Okay? That becomes the standard deviation of your difference sampling distribution. Now, I'm going to do a little bit of algebra here, so bear with me just for a second. Now, what does that look like? What is the standard deviation of this particular single proportion sampling distribution? And that's where we take P times 1 minus P. Okay, well, I'm going to do it out here. It's supposed to be the square root of P times 1 minus P all over N. But then we're squaring it, right? So we're taking this and we're squaring it. And so and since squares and square roots cancel each other out, we're left with P1 times 1 minus P1 all over N. And then we have to add into it this guy. And it would be the same thing. Right? It would be P2 times 1 minus P2 all over N. We're supposed to square root that, but then this says to square it because we want the variance. And since squares and square roots cancel each other out, we're left with P2 times 1 minus P2 all over N. And so this becomes your standard deviation of your sampling distribution of the differences. Okay? And so that is what we would need in for this guy right here. Okay? Now, this is the standard deviation of the sampling distribution of the differences. Standard error then would simply be replacing p with p hat. And so that would look like the square root of p1 hat, I'm trying to get this in here, p1 hat times 1 minus p1 hat all over n plus p2 hat times 1 minus p2 hat all over n. Okay? So that becomes the standard error for your confidence interval. Okay? And again, just call it standard error because we're using our sample value, p hat, instead of the population p, because we don't know what p is. Okay? All right, so we're starting to develop the formula for this a little bit. And so what is this going to look like by the time it's all said and done? Okay, our point estimate, again, excuse me, our statistic is going to look like this. We're talking about the difference. We're trying to estimate the difference. So we're going to take p1 hat minus p2 hat plus or minus some critical value. Remember, it's tied to your confidence level. Times, and then the standard error calculation, which is from up there. p1 hat times 1 minus p1 hat all over n plus p2 hat times 1 minus p2 hat all over n. Okay? And that becomes the general form of your confidence interval to estimate the difference in true population proportion between two groups. Okay? So a little bit more complicated formula. The good news is the calculator will do all that for us, and we'll get to that a little bit later. Okay? Now, so let's go through and talk a little bit about the conditions for calculating a two-sample z-interval. The same conditions apply as the conditions we had for a one-sample z-interval or one proportion z-interval, only you have to check it for both samples. So your random, normal, and independent checks are going to be the same, and we're going to look for the same things, but it needs to happen for the two groups. Okay? So let's walk through an example here to see what's going on. So many news organizations conduct polls asking adults in the U.S. if they approve of the job the president is doing. How did President Obama's approval rating change from August 2009 to September 2010? According to a CNN poll of 1,024 randomly selected U.S. adults on September 1st to 2nd on 2010, 50% approved of Obama's job performance. A CNN poll of 1,010 randomly selected U.S. adults on August 28th to the 30th on 2009 showed that 53% approved of Obama's job performance. Right? So the first question is, it's different, right? So it's gone down. His approval rating apparently went down, but it went down by 3%. And so the question we have to ask ourselves is, could that have happened by random chance, or does that truly indicate a difference in his approval rating? Okay? And so part A here says explain why we should use a confidence interval to estimate the change in Obama's approval rating, rather than just saying that his approval rating went down 3 percentage points. Okay? And then we're going to construct and interpret a 90% confidence interval, and based on that interval, we're going to talk about if there's convincing evidence that Obama's job approval rating has changed. So first things first, to answer to A, why do we need a confidence interval to estimate the change? Well, there's sampling variability, right? And now there's added sampling variability between, because there's two samples now, and each one has their own variability. So while 53% and 50% were from random samples, we understand that if you sample again from the same population, you're likely to get a different approval rating. So these are not necessarily the true proportions, 53 and 50. Okay, they could be further apart. They could be closer together. The 2009 approval rating could be higher than the 2010, depending on who was sampled and who you talked to. So that's why we need to use a confidence interval. A confidence interval should give us a better idea of the difference in these two, right? And so that's what we're going to do. So part B. Let's go do our confidence interval, right? And again, in the form of our state plan, do conclude. State first. What is it that we're trying to do? We're going to create a 90% confidence interval to estimate. And you need to define the difference. We're going to estimate the proportion in 2010 that approved minus the proportion of 2009. So we want to know the difference in the approval rating. And we can define it as the approval rating in 2010 minus the one in 2009. You can switch those if you'd like, as long as you understand what your confidence interval is telling you. The order does not matter. Okay? And then we have to define what P is. We've got to let everyone know what P is, because they may not have the background information. You're going to file a report based on your findings, and so you've got to tell everybody what P stands for. And here, P is the true proportion of all U.S. adults who approved of Obama's job performance in September 2010 and August 2009. Okay? It's even more specific than that. It's the true difference in the proportion of all U.S. adults who approved of Obama's job performance in 2010 versus August 2009. I think we need to change that up a little bit. Okay? That's what that subtraction tells us. Okay? So, we go through our process. We're going to plan it out. We're going to use a 2 proportion Z interval to do just that. And so we want to make sure that we're letting everybody know that. So we're going to do a 2 proportion Z interval for this difference in job approval rating from 2010 and 2009. Okay? Before we get to do that, we have to check our conditions. Okay? So, first and foremost, random, right? And this is like it was before. The data need to come from random samples. And both sets of data need to come from random samples. Okay? And they do. It was stated, so we can move on. Normal. Now, both sampling distributions for 2010 and 2009 need to be approximately normal. Okay? And so we got to make sure that we're checking both. And so our n times p and our n times 1 minus p both need to be bigger than 10 for both sets of data, for both samples. Okay? And you see there. Okay, so again, we're going to have to use p hat, right? We don't have a p, so we have to use p hat. And the good thing is, for our intervals, we can just count successes and failures if we have them. Unfortunately, here we don't. So in the 2010 poll, 50% approved. So 0.5 times the 1,024, 0.5 times the 1,024, both of those are bigger than 10. And then your p hat for 2009, which was 53%, so 0.53 times 1010 and 0.47 times 1010 gives you 535 and 475 there. All of those are bigger than 10, so we can assume that all of our successes and failures, not assume, that they're bigger than 10, and so we can assume that our sampling distributions are going to be normal. And the reason why we care about the individual sampling distributions is, like we said before, when you combine these two, the combination distribution is going to be approximately normal as well. Okay? And that leaves us with our independent check. And each sample, one, had to be taken independently, and we can assume they were since they were a year apart. And we have to make our sample size assumption, or our population size assumption, for both sets. So 1,024 from 2010, we have to assume there were more than 10,240 adults to sample from, which is safe. And in 2009, we had to assume that there were more than 10,100 adults to sample from, which is safe. Okay? And so that gets us into, once our conditions are met, and they have been met, we can start constructing our interval. Okay? And so again, as a reminder, from where this is coming from, you have the formula in your notes previous, but I'm going to write it out again. Okay? So we're looking at taking P1, actually we'll define it as P 2010 hat minus P 2009 hat plus or minus your Z star, okay? And this critical value came from the same place it did before, right? You can either do inverse norm, or you can use table A, but you have to think through. It's a 90% confidence interval, so we're going to look for the Z-score where 95% of the observations are less than that. And if you need a review of that, let me know. We'll talk about it. And then, of course, this is coming from your standard error calculation, which is P hat 2010 times 1 minus P hat 2010 all over N, and I'm going to leave that, and the other side's going to be for 2009. Okay? So that's where the calculation's coming from. You can start just sort of number crunch at this point, right? So the difference is negative 0.03. This is our margin of error, 0.036. And so our interval turns out to be negative 0.066 to positive 0.006. Which means, and that's what we got to tell everybody now in our conclude step here, right? So we are 95, not 95. This is a typo. We are 90% confident that the interval from negative 0.066 to 0.006 captures the true change in the proportion of U.S. adults who approved of Obama's job performance from August 2009 to September 2010. And so there's a little bit of a difference in the wording here, right? Because that's letting us know how the approval rating changed from one year to the next. Okay? Your conclusion obviously needs to come from what it is your interval is supposed to be representing. And right now it's the true change in the proportion. You can say the true difference in the approval rating for President Obama of the U.S. adults from 2009 to 2010, something like that. You can always find some different wording. So what does that really tell us? What information is that really giving us? Okay? What that really means is that it's plausible that his job approval had fallen by up to 6.6 percentage points, right? Because a negative value indicates that his 2009 approval rating was higher than his 2010. So it's plausible that his job approval had fallen by as much as 6.6 percentage points, or it's plausible that his job approval rating had increased by as much as 0.6 percentage points. Okay, that's what our interval is letting us know. Okay. All right. To answer our last question, question C, which was based on your interval, is there convincing evidence that Obama's job approval rating has changed? Right? Well, now 0 is included in the interval. And if his approval rating hadn't changed, then when you take the difference from 2009 to 2010, the difference would just be 0. So since 0 is in our interval, it's possible, and not even possible, it's plausible. We can even change that word, right? It's plausible that there had been no change in his approval rating. Therefore, we do not have convincing evidence that his approval rating had changed, right? And so we're using the interval there to help test a claim, and we'll actually test claims in the next set of notes. So that's it. That's your interval. Okay, and again, like I said before, not a lot different from a single proportion. Just some calculations are a little bit differently, and then what the numbers tell us is a little bit different as well. So you've got to be very conscientious about what our numbers are trying to let us know. Okay. Okay, we'll stop there. We'll do a quick calculator check tomorrow. We'll run through the same example, and I'll walk you through how to use the calculator, and then we'll get to your homework. Okay? So that's it. Enjoy the rest of your evening. We'll see you guys in the next class period.